Hello and welcome to our today's webinar called Role of Fatty Acids in Metabolic Dysfunction Associated Fatty Liver Disease and Concomitant Cardiovascular Risk. As you know, cardiovascular diseases represent a significant public health concern, but even more important healthcare issues, cardiometabolic complications, accompanying a great variety of inflammatory and immune diseases. Abdominal obesity, type 2 diabetes, hypertriglyceridemia, and hypertension are individual factors that contribute to liver function impairment. I believe many of you are familiar with the term non-alcoholic fatty liver disease, NAFLD, which has been recently replaced with a more accurate definition called metabolic dysfunction associated fatty liver disease, MAFLD. MAFLD is a very common complication of the earlier mentioned conditions and can progress to liver fibrosis. While commonly present, MAFLD doesn't have disease-specific treatment, and typically patients advise on eliminating or decreasing risk factors and pharmacologically treating main diseases. Although some of the non-specific pharmacological treatments affect pathophysiological mechanism of NAFLD, such as angiotensin receptor blockers, newly developed sodium glucose cotransporter 2, CGLT2 inhibitors, and other drugs, there is still a remaining need for further research in the field. Considering that these cardiometabolic complications involve lipid abnormalities, predominantly hypertriglyceridemia, recent progress in fatty acids research and clinical application of omega-3 fatty acids for such conditions is of great clinical importance. Moreover, anti-inflammatory bioactive lipid mediators derived from the omega-3 fatty acids represent an interesting avenue to explore. With that, I would like to introduce our first speaker, Dr. Tricia Grumman-Goyette, who's an assistant professor at the University of Copenhagen, and her work focuses on determining biological functions of different fats, such as omega-3 fatty acids, and their metabolites in cardiometabolic diseases. Her work spans biochemistry and physiology to understand the necessity and utility of fatty metabolites in health and disease, such as atherosclerosis and fatty liver disease. And with that, I'm giving the talk to Tricia. I'm going to go. Thank you.
Thank you for the opportunity to tell you about some of my work around fatty acids and cardiovascular disease. So I'm actually going to very quickly cover two different but important uses of fatty acids in cardiovascular disease. First, I'll go through the importance of fatty acids as a fuel source in the heart, and then I will cover a bit about how specific fatty acids can be used to improve cardiometabolic health. So cardiovascular disease is the #1 cause of death worldwide. In fact, nearly 1 in 3 adult deaths is caused by heart disease. And heart disease is a broad term encompassing coronary artery disease, myocardial infarction, and even congenital defects. So risk factors for heart disease include hypertension, high cholesterol, diabetes, and obesity. So diet and environment are key elements in disease development. And this complex etiology of the cardiometabolic diseases means that we need to take this challenge tackle this challenge from multiple angles. So let's start with looking at how altering metabolism in the heart actually affects its function. So the heart is constantly beating, therefore it has a constant demand for energy. And a normal, healthy heart gets the majority of its energy from fatty acids and makes up the remainder by using glucose. So importantly, the heart can alter these ratios and even use other substrates like amino acids or ketones or pyruvate, depending on what's available. This ability to use different substrates for energy is termed metabolic flexibility, and it's important for the heart to adapt to different conditions. Several disease states diminish the metabolic flexibility of the heart and compel the predominant use of a single substrate. So the diabetic heart becomes insulin resistant, diminishing its ability to take up glucose. The heart then increases its uptake of fatty acids and uses these fatty acids for energy, but also stores the excess triglycerol. And the accumulation of excess lipids can exacerbate insulin signaling, insulin resistance, and diminish contractile function, which is known as diabetic cardiomyopathy. And then contrary to diabetes, with ischemia, hypertrophic or failing hearts increase the use of glucose for energy. In the case of ischemia, a portion of the heart is cut off from oxygen and so must perform anaerobic glycolysis, which is highly inefficient compared to oxidative phosphorylation. In hypertrophy and failure, glucose can be oxidized, but the question remains of whether the altered metabolism is a compensatory mechanism or if it exacerbates the disease when the heart cannot switch back to the normal ratio of fatty acid to glucose use. So to study the importance of substrate preference and metabolic flexibility in the heart, I studied an enzyme that activates fatty acids by adding the coenzyme A to them. This addition allows the fatty acid to then be incorporated into more complex lipids like phospholipids, triglycerols, as well as be converted to other lipid mediators. Additionally, the conversion of the fatty acid to an acyl-CoA allows the fatty acid to be used in beta oxidation for ATP generation. And this is the side that we'll focus on here. So I used an inducible knockout of ACSL1, the main acyl-CoA synthetase in the heart. And without that enzyme, the hearts lost 80% of their ability to generate long chain acyl-CoAs. But this had no effect on the heart's ability to form triglycerols and did not change the levels of phospholipids at the class level. However, it did have an effect on oxidation of fatty acids. So here I can show that oxidation of palmitates, which is saturated fatty acids, is diminished by more than 90%. So we've also found that uptake of a fatty acid analog, bromopalmitate, which cannot be broken down, is 75% lower in the knockout hearts, showing that the addition of the coenzyme A group is necessary for the retention of the fatty acid within the cell. Despite this lack of fatty acid oxidation, the hearts continued to beat normally and had normal systolic function. So we know that they're able to make enough ATP for this. Therefore, the hearts are getting their energy from a different substrate. So here I can show that there's an 8-fold increase in uptake of 2-deoxyglucose, which again cannot be oxidized, indicating that glucose metabolism is highly upregulated with the loss of ACSL1 and the decrease in fatty acid oxidation. Along with that, pyruvate oxidation was also 2-fold higher, indicating an increased flux through the TCA cycle. So the hearts can compensate for the lack of fatty acid oxidation in terms of ATP generation, but we questioned how this huge impairment to metabolic flexibility would affect the hearts. So I mentioned that contraction or systolic function is normal with limited fatty acid oxidation, but these hearts are enlarged. Additionally, they display diastolic dysfunction, meaning their ability to relax is impaired. And we linked this hypertrophy of the heart to activation of mechanistic target of rapamycin 1, or mTORC1, which is a serine threonine kinase that regulates cell growth and proliferation. So we then treated the animals for 2 weeks with rapamycin, an mTORC1 inhibitor, and then this decreased the activation of mTORC1, as seen here through the phosphorylation of S6 kinase, and found that the hearts from both the control and the knockout animals were significantly smaller than the vehicle-treated animals, and that the knockout hearts were no longer hypertrophied. And so this shows that the hypertrophy was due to the mTORC1 activation, but we wondered what other effects chronic activation of mTORC1 would have on the ACSL1 knockout hearts. So mitochondria are incredibly important to health of the entire cell. And so we wanted to determine if loss of ACSL1 and that impaired fatty acid oxidation would impair the structure function of the mitochondria. So here we used electron microscopy to examine the cellular architecture and mitochondrial structure at incredible magnification. So we can see the organization of the muscle, the striations, the Z bands and I bands, and the ACSL1 knockout hearts have normal muscle structure, but the mitochondrial structure is not preserved. We see many mitochondria are swollen or vacuolated, and as we can see that here pointed out with the white arrows, and they also have disrupted inner mitochondrial membranes. And so because we saw these abnormal mitochondria in the knockout animals, we questioned whether or not the function would also be impaired. So using permeabilized cardiac muscle fibers to measure mitochondrial respiratory function in minimally disrupted cells. Then we measured basal oxygen consumption, which was not different between the control and the knockout. But when we stimulated the mitochondria with ADP, a signal for low energy, the knockout mitochondria consumed 30% less oxygen than the controls, indicating an impaired ability to respond to stimuli and a distinct functional impairment. So when thinking about the mTORC1 activation and mitochondrial defect, we thought about how mTORC1 takes signals of sufficient energy like glucose 6-phosphate or amino acids or insulin, and then translates them into growth. And so one way that mTORC1 promotes growth is by inhibiting autophagy. And autophagy is there to clear proteins and lipids, as well as to remove damaged organelles. So with this inappropriate activation of mTORC1, we do not have normal formation of the autophagosome and thus impaired degradation of the damaged mitochondria. And so we wondered if this impaired autophagy that we likely see in the ASS01 knockout hearts is also impairing the mitochondrial health. So we treated the mice with an mTORC1 inhibitor called rapamycin, and then examined the mitochondrial structure and function. So just a reminder, in the untreated knockout, we see that many mitochondria present with vacuoles and disrupted cristae. But if we treat the animals with rapamycin for 1 week, we find many autophagic vesicles, and see that some of the abnormal mitochondria have begun to decrease. At the end of the treatment, which was 2 weeks in this case, we see a few autophagic vesicles and more normal mitochondrial structure, indicating that once the worst mitochondria have been cleared, the autophagic vesicles can dissipate. And this allows autophagy, thus allowing autophagy to increase, has cleared the damaged mitochondria from the hearts. So now that we know we can clear damaged mitochondria by inhibiting mTORC1 with rapamycin, we wanted to determine whether mitochondrial function was also improved with rapamycin treatment. Again, we see that there's the low ADP stimulated oxygen consumption in the knockout, and this rate was not improved with rapamycin treatment. However, if we incubate the mitochondria with FCCP to stimulate maximal respiration, we find that rapamycin has normalized this value, indicating that there's an improvement in mitochondrial function there. And again, this was only a 2-week treatment, so there's the possibility that a longer treatment may have helped out that ADP stimulated respiration. So to put it all together, in normal hearts, ASS01 is activating fatty acids, and many of these fatty acids are then oxidized for energy. However, with loss of that enzyme, we decrease beta oxidation, and the heart compensates by increasing glucose use. This leads to increased glucose 6-phosphate content, which can then activate mTORC1. mTORC1 then is responsible for the hypertrophy of the hearts and also inhibits autophagy. And this is decreasing the clearance of damaged mitochondria, leading to an accumulation of abnormal mitochondria with an impaired maximal respiratory capacity. And so we were unable to improve the ADP stimulated oxygen consumption with our short treatment, and also potentially due to other alterations in the metabolism of the cell. But overall, we have the ability to use fatty acids for ATP generation. We see that it's important beyond the energy derived, and this is due to the effects of the use of other substrates. So I'm going to change topics a bit from the importance of breaking down fatty acids for energy to how we can use specific fatty acids to improve cardiometabolic health. So the fish oil type of omega-3 fatty acids, including EPA and DHA, have been considered heart healthy for many years due to their improved cardiovascular health in populations with high fish intake. And the association between high omega-3 intake from supplementation and cardiovascular disease-associated mortality has yielded some mixed results, likely in part due to the type and the amount of fatty acid used, length of study, as well as potentially other factors, including concurrent statin use to lower cholesterol. But overall, there is a small reduction in risk with omega-3 use. And this, along with the longitudinal diet studies, have shaped the recommendation to replace saturated fats with polyunsaturated fats, especially with a focus on the omega-3 fatty acids. So how do the omega-3 fatty acids reduce risk? So they're likely reducing chronic unregulated inflammation associated with obesity, both through pro-resolution molecules that are made from the omega-3s, as well as reducing the pro-inflammatory molecules that are made from the omega-6 fatty acids. Omega-3 fatty acids also change the membrane properties of a cell and reduce oxidative stress, in addition to reducing thrombosis and helping to regulate heart rate. This is, of course, comes with the caveat that high-dose omega-3 supplementation may increase the risk for atrial fibrillation. And the mechanism that I focus on most is reducing triglyceride-rich particles, as elevated triglycerides are an independent risk factor for cardiovascular disease. So lowering triglycerides can be done by increasing oxidation of the fats through activation of PPARs, or that can be done through reducing VLDL secretion from the liver, or reducing lipid uptake from the intestine. And the molecular mediators of these actions are still under investigation. And so that's where my group is coming in now. So my group analyzed plasma from people who consumed EPA and DHA supplements for a year and found novel metabolites that were upregulated. So these were the EPA and DHA containing N-acyltaurines, or NATs. NATs are a conjugate of the fatty acid and taurine, and these are synthesized in the liver by the same enzyme that adds glycine or taurine onto bile acids. So they're also degraded by fatty acid amide hydrolase, or FA, the same enzyme that hydrolyzes some of the endocannabinoids such as anandamide. Additionally, NATs have a very high turnover rate, and the DHA containing NAT goes up approximately 100-fold in the liver within 3 hours if its degradation is inhibited. So these are pretty promising molecules, but their functions have been largely ignored until recently. But to study the function, we went to mice fed fish oil. So we see similar increases in plasma as we did in humans, but with mice, we can check the bile too. So here, after just 3 days, the amount of the DHA containing NAT, or C22.6 NAT, as I tend to call it, goes up to 1 millimolar, which rivals the concentrations of many bile acids. So of course, with that, we wanted to check how having that amount of the NAT in bile affects bile's main function, emulsifying dietary fat for lipid absorption. We gave mice fed those same diets, an LPL inhibitor to prevent uptake of triglyceride into tissues, and then administered an oral gavage of oil. So in the fish oil fed mice, the plasma triglycerides were lower after that oil, giving the possibility that these NATs are having an effect in bile. We then tested the NAT through direct administration. So when mixed into the oil, C22.6 NAT prevented uptake of dietary fat. And this was due to impaired hydrolysis of the triglyceride, as the free fatty acid is taken up normally when mixed with NAT. But interestingly, the other tested NATs, so the oleate and the arachidonic containing NAT, did not have the same effect. So it's something specific to this fish oil type, the omega-3 fatty acid derived NAT. So we wanted to further investigate the effects of chronically elevating C22.6 NAT, and we used a genetic model that cannot break down NATs, the FAH S268D mice. So these knock-in mice have a point mutation, which puts a charge in its active site, preventing the charged taurine from entering, but allowing the uncharged substrates, such as anandamide, to be hydrolyzed. So we combined this model with a high-fat diet plus or minus fish oil, and found that we could elevate C22.6 NAT even further than in the wild type, up to 4 millimolar. So that's 4 times higher than in the wild type. In this model, the C22.6 NAT in the bile also decreased lipid absorption after an oil meal. Importantly, this change in lipid absorption did not impair weight gain, so they did not experience any kind of calorie deficit. When investigating the metabolic effects of high omega-3 NATs, so like 22.6 NAT, and the altered lipid absorption, we found that the plasma triglycerides were lower in the knock-ins on both diets, as well as the wild type fed fish oil diet. But the most striking effect was actually in the liver fat accumulation. So the knock-in, the mice that cannot degrade NATs and have high endogenous levels of C22.6 NAT had very low amounts of triglyceride in their liver. And this is very similar to the levels found in chow-fed mice, despite having been on a high-fat diet for 6 weeks. So this went far beyond the effect that we see in the wild type, giving an indication that C22.6 NAT might be important in this regulation. So then, to determine if C22.6 is indeed the effector molecule, we fed mice a high-fat diet while treating for 2 weeks. with the NAT directly. So this direct treatment led to reduction in both plasma and liver triglyceride when fed a high-fat diet. But if we fed a high sucrose diet instead, which eliminates the lipid absorption as a necessity for the accumulation of fat in the liver, and instead forced de novo lipogenesis, we found that treatment with the NAT had no effect on plasma or liver triglyceride, indicating that the NAT works at least partially through inhibiting lipid absorption. So in summary, C22.6 NAT can be part of the mechanism of omega-3 induced triglyceride lowering through slowing or reducing dietary lipid absorption to then reduce liver fat and also potentially enhance GLP-1 secretion, contributing to better overall metabolic health. So our lab is also working to check these results in an atherosclerosis-prone model, as well as a small clinical trial to ensure the translational value of this work. So with that, big thanks to all those who contributed to this work, especially Sam Trammell for all the NAT measurements. And then the first part of my talk was from my PhD work in Rosalind Coleman's lab at the University of North Carolina. Thank you all for listening.
Thank you very much, Dr. Gruengoed. So I think we have Q&A session scheduled in the end of the webinar. So if you don't mind, we'll move to the next speaker. And then if you have any questions, as mentioned, you can put them in the chat box or ask directly in the end of the webinar. Thanks again, Dr. Gruengoed, for sharing your results and your insights on this research. And then I'm happy to introduce our next and final speaker, Dr. Yu Zhou, who is a lecturer at the Systems Immunity University Research Institute and the Division of Infection and Immunity, Cardiff University, an adjunct professor at the Faculty of Medicine, University of Helsinki, and also the chair of the British Society for Immunology South Wales Regional Group. His research interest is developing and using data-driven approaches to understand metabolic inflammation, focusing on but not limited to fatty liver disease. In that, please, Dr. Zhou, if you're ready, please go ahead and share your presentation. Thank you.
Hello, everyone. So so today my talk is about the lipids in the MDPI and genetics associated fatty liver disease. So as you can see, because for the MDPI, this is a new name for the fatty liver disease, which was originally called non-alcoholic fatty liver disease. So they have, as you can see now, many different environmental factors or genetic factors can cause disease, including the dietary factors, lifestyle factors, and also some, like for example, the gut microbiota, as well as some genetic factors. The whole disease is the pathogenesis of the disease is like from healthy liver to steatosis, means fat accumulate in your liver, and if it keeps progression, it will have the inflammation, ballooning, and fibrosis in your liver, and cause liver injuries. As you probably realize, the disease now has been highly associated with type 2 diabetes as well as the cardiovascular disease. And the severity of the disease now is the leading cause of the liver transplantation. And recently, the ESD and ASD recently proposed a new name for the disease called MDPI. It means metabolic, associated fatty liver disease. So as you can see, there are a variety of metabolic factors can cause disease, including the prediabetes or obesities, like the higher BMI, and hormone more than 2.5, and the lower high density cholesterol and high level of triglycerides, with increased blood pressure. So all those factors contribute to MDPI, and also of the gut microbiota has been an important risk factor for MDPI disease. The disease actually is the leading cause of the hepatocellular carcinoma, as you can see the red ones here. So for the last 20 years, as you can see, the NFLD or LASH is increasing a lot from a small proportion to a high proportion in 2010. And MASH, or we can call it LASH, I mean, it's like the metabolic associated steatohepatitis. So it's become the leading cause for transplantation in females, and second leading indication for the males, as you can see here. Particularly regarding healthcare cost, it imposed a big economic burden for our healthcare systems. For USA, Germany, France, Italy, United States, United Kingdom. So the whole cost is about 35 million pounds per year. Per year for those countries. Impose a big burden for the healthcare system. So today, I will quickly overview like 3 parts of the disease. So the first part is onset of the disease, because this is a lot about the biomedics meeting. So I will focus on our previous work focus on the lipids and also fatty acids related to the disease. So here is this is my when I was doing my PhD, I worked in WHO for some time. So together with Joe Breda in the World Health Organizations in Denmark. So you can see here from the 1961 until 2007. So for those 40 years, you can see how the different saturated fatty how it has been consumed in different countries. So the red means the higher amount of the how amount to consumer, and the blue means lower ones. Sorry for my computer. Yeah. So you can see for some countries it has increased to consuming the saturated fatty acid. For some countries it become lower. So here you can see the prevalence of the overweight and obesity across the 56 European member states. So basically, obesity and overweight are very, very prevalent across all for our European countries. Only several countries maybe has a lower, has a lower prevalence of the overweight. For example, the overweight prevalence. So this indicates the doubt or is very important, and also raise the questions whether the saturated fat has any specific or what's the role of the saturated fat adult for our human health. So in 2018, we had this design list RCT, clinical trials to give the people subjects like 38 subjects unsaturated fatty acid food and saturated fat food and carbohydrate food, and this trial has went for about 3 weeks. And here is the diet compositions that you can say unsaturated diet, including olive oils, saturated including butters, and then we will observe then we try to assess the liver fat amount and other functions for the livers. So here are the results. So you can see regarding the liver fat amount was increased by all the diets, but saturated fat adult increased liver fat more than other diets in our human bodies. For the as you can see here, clearly a very significant ones. So furthermore, we strive to think what are the mechanisms was involved underlying our observation. So we measure, for example, also the HOMA-OIRs, a very important indicator for the type 2 diabetes, and the different lipids, for example, the plasma ceramides in the plasma, ceramides in the plasma. So the saturated acid, don't know how to control this one, so it's worth change. Saturated acid is clearly increased the plasma concentrations as well as hormones compared to other unsaturated fatty acid diet and carbohydrate diet. Also, the microbiota, according to data here, you can see the endotoxin meal increased in responding to the saturated fatty acid diet. So the serum acid is increased, and also different pathways has been activated according to different types of diet. Especially for saturated fatty acid, you can say, for example, some like the PBA gamma signaling pathways, and also the unsaturated fatty acid pathways. Those pathways are changed across different types of diets. So clearly, you can see the saturated fatty acid shows more harmful effect compared to other two diets, which really raise the question. We need to be cautious when we have different types of diet. The second part, I will quickly give you some introduction of our the development of the disease. So for the statostasis, you can see now two types. One is called massivity, usually associated with the metabolic factors, for example, like obesity, type 2 diabetes, and cardiovascular disease factors. So those factors are also important for the metabolic syndromes. And there's another types of the fatty liver disease. We can call it genetics associated fatty liver disease. So which means it was caused by the genetic factors. So one of the most common genetic variant called the PMPR3 variant. So this variant is about in about 40% of the Europeans. So for these ones, it's also associated with many with some metabolic factors, but it's not associated with the insulin resistance and the cardiovascular disease factors. It also can cause the large cirrhosis or hepatocellular carcinoma, yeah, but a lot of other two, cardiovascular and type 2 diabetes. So what are the difference? What are the why they have such a difference, and why it causes difference? In order to understand the mechanisms behind it, we performed lipidomics analysis. So what we have done is we have connected 125 liver biopsies. So we have divided into different groups. One we can call the low HOMO or high HOMOs, according to the HOMO factor, and also another one according to the genetic factors, PMPR3 variant, no variant or no variants. So we will try to match the cases and controls. As you can see here, basically they are not much. They have the same proportion for the gender and BMI, and so we can call each group. One group is called MAFD, and another group we can call it GAFD. So they have the very similar liver histology, as you can see here, in terms of macrovascular liver fat, as well as the large percentage. Yeah, okay. So basically, those factors are has very similar difference according to the in terms of MAFD or GAFD. And then what we did, we trying to think what's the definition code underlying those two types of fatty liver disease. What we did, we developed a lipidomics analysis pipeline. So as you can see here, according to our results, they have very different triglyceride profiles between MAFD and genetics associated fatty liver disease. Probably you can recall just now I show the liver fat difference, liver fat amount difference, large percentage difference are very similar for those two groups, two diseases. But here, clearly, the triglycerides show the difference. For the high with no HOMO groups or MAFD groups, you can see that is very high amount of the saturated fatty acid or monounsaturated fatty acid here. And in the GAFDLD, they have a higher polyunsaturated fatty acid, polyunsaturated triglyceride here. So sorry, forgot to mention. So for the x-axis, it represents the double bond with triglycerides. For the y-axis, it represents the numbers of carbons. And the red means increase and blue means decrease. Star indicates the significance. So you can see the significance. You can see how it looks. The heat map shows different profiles of triglycerides in MAFD and GAFD. Furthermore, we did in vitro experiments using the whole cell hepatocytes to look into the PMPR3 variant lock-in or lockout cells. So in the PMPR3 lockout cells, clearly they have an increased of the polyunsaturated fatty acids compared to the wild types, which fits well with our human lipidomics data from human livers. Okay. Furthermore, besides the triglycerides, we also look into ceramides. So ceramides show also the very different profiles in MAFD compared to GAFD. So in the MAFD, you can see there are a few ceramides increase, which are most are the dihydroceramides, but for the GAFD, there are no any significant difference for in responding to the disease progression. Yeah, similarly for the X, means the sphingomyloid base, and for the Y is the number of fatty acid chain. So we further propose maxims underlying the MAFD and GAFD. So we believe, actually, according to our data, that the dihydroceramide synthesis matters, or we can say this pathway dissociate the MAFD from the GAFD. So as we can say, the hydroceramide increase and hexaceramide sigma have no changes. So that's why we think this pathway matters rather than the other two ceramide pathways, finger-burning hydrolyzed pathways and switching pathways. And also, according to the maxims, adiponectin can clearly affect ceramide levels. So we further measure ceramides from the, we further measure adiponectin from the blood of those patients. So as we expected, in the high and low hormone groups, you can see the adiponectin levels decreased, but there was no difference in the genetics associated fatty liver disease, which really confirmed our findings in lipidomics through the lipidomics. So the conclusion here is triglycerides are much more saturated in the MAFD compared to GAFD, and the polyunsaturated triglycerides are enriched in the GAFD. And the lower ceramide synthetic pathways matters, or can say dissociate those two different types of the fatty liver disease. Let me check my time. I think I still have some time or not. Alex, did I run out of time or?
No, yeah, I think you could like 4 or 5 minutes more.
Okay, yeah. So I can quickly talk about a bit more about the diagnosis of disease using the lipidomics. So as I mentioned, NASH, or can say MASH, is a severe status of the fatty liver disease, which means it has a ballooning necrosis, inflammation, fibrosis, and is the leading cause of the liver transplantation and highly associated with the cirrhosis and liver cancer. And the prevalence is also very high for the NASH. However, for the steatohepatitis or MASH, at the moment, lateral MASH, there's no any very very good way to diagnose it. The golden standard is lethal biopsies, which is invasive and cost some money. And also, no study can state the genetic variations, for example, PMP3 variant, and no study has externally validated has been trying to validate the diagnosis score, externally. So what we have done, we have used a machine learning approach to develop a model based on our lipidomics data. So as you can see here, we can show many different lipids show different concentrations across the NASH and status disease and control. And we can cluster those those lipids to eight lipid clusters. And especially you can see the significant difference is in cluster 3, 4, and 6. The 3 represents sphingomyelins, 4 represent the saturated and monounsaturated triglycerides, and 6 includes all those lipids related to lysol, phosphatidylcholine. So based on the results from those 3 clusters, we further selected 3 lipids represent those clusters. So finally, we developed this diagnosis score. So we used 3 routine clinical measurements: AST, insulin levels, and PMP3 variants, including those 2 lipids as well as 2 metabolites, glutamic acid and isoleucine. So our diagnostic, our method showed very good performance with a higher AURC area compared to other scores, as we can see here. So the red is our performance of our represent performance of our diagnostic score, and other ones represent other scores. And this has already been highlighted in the Daily Express. And furthermore, this method can be directly used through our online portal. So if you type, for example, CG45 or different measurements based on AST, insulin levels, and all the other lipids, so it can be used to define whether the patient is highly likely to have MASH or NASH or not. Okay, so this is my final slide. Thanks for all the people in my group and also the collaborators. Thanks very much for your patience. Thank you.
Thank you, Dr. Zhou. Great talk. So I think now we can move to questions. So I haven't seen any questions so far in the chat box. So let us know if someone like attendees want to speak or want to put some questions. And if not, so maybe we can start with something like a panel discussion. So actually, I just want to wrap up these 2 great talks into like general comments and suggestions for the future research and clinical practice. So I have one question to Dr. Grimm-Goyette. So Tricia, maybe you can comment on the like application of fatty acids for heart failure treatment. As you know, you mentioned like all these metabolism changes and implication of fatty acids in mitochondria, energy production. So I know that there being like a couple of big clinical trials before, and I think they were probably not so significant. So maybe you can comment just on the future and the current potential implication of fatty acids for heart failure treatment. Thank you.
Yeah, so we know that fatty acids are going to be it's going to be very important which type of fatty acids. So I guess you're thinking like the polyunsaturated fatty acids, like omega-3 types of
I believe
fatty acids.
Yeah.
Right. So in terms of omega-3 fatty acids and the supplementation trials that have gone on, like the Reduce It trial, which used just basically a purified EPA, that showed significantly reduced cardiovascular disease mortality, right, with the compared to their control, whereas the recent Strength trial, which was a mix of EPA and DHA, did not show that significant effect. And so this is pushing people to think that maybe it's EPA that is potentially a more active and more beneficial, and we need to do that 4 grams per day of EPA instead of a mix of DHA and EPA, but we know that they have different beneficial effects. It just depends on what you're looking for. But in terms of the clinical trials, EPA has been more promising so far. But it's the mechanisms I think are still up for debate. What the benefit is. There are potentially many, because we know omega-3 fatty acids have many do many things within the cells. They incorporate into membranes, they activate PPARs, they are themselves oxidized. So lots of potential there.
Okay. Thanks, Tricia. So Dr. Joe, do you have anything to comment on these?
Yes, actually, I have questions regarding the Dr. Greenfield talk. So you look into the PFAs, right? The omega-3 fatty acids in the cytostasis. Did you also look into their effects on the immune cells, for example, for the inflammation, specifically regarding inflammation? Sorry, if you have done it. Maybe yeah.
We actually have not looked at the effects of like the DHA containing NAT. That's what you're referring to, right? We haven't looked at the effects on immune cells yet. It's something we've definitely thought about, and we're wondering if it can actually be used by some of the same enzymes that are generating the SPMs, and if it's going to affect that. We know that the arachidonic acid containing NAT can be used by some of those same enzymes that use arachidonic acid. So it's an interesting avenue for us. We haven't gone down it yet, but it's something I'd be interested in for sure. Because adding that taurine on does change the chemistry of the molecule because it's charged. So not all enzymes are going to like that, but some are able to use it, at least with the arachidonic acid. So there's potential. But we don't know if it's activating any other specific receptors. Some of the other NATs can activate different GPCRs or TRP receptors. But in terms of PPARs, we haven't seen much yet. But some of the other receptors that are possible with the PUFAs, we don't know yet. And immune cells are of course very interesting. Immune or inflammation regulation is of course very interesting.
Thank you. Because I remember in your first part you talk about the mitochondria function. So that's why, because for the steatohepatitis, recently a few papers say mitochondria function is very important for this steatohepatitis. So that's why I was thinking the treatment with the fatty the omega-3 was fatty acids on.
Of course, omega-3s can help to regulate mitochondrial function and number, and so something to explore further, because we know mitochondria are incredibly important for maintaining the ATP generation within a cell. I mean, heart, of course, is what I was talking about, but hepatocytes as well. I mean, hepatocytes are doing a lot of things that require ATP as well as the other. There's lots of other functions of mitochondria too, but we think about them as the powerhouse of the cells, of course.
Thanks very much. Very interesting.
Thank you.
Thank you. Dr. Joe, actually, I have now a question for you. So you mentioned this on your presentation that there are some issues with MFLD diagnosis. So are there any novel promising markers for MFLD, and what is, you think, your the future perspective on this? If you can.
Yeah, for the MFD actually, it's a complex disease. So it's including the simple steatosis with fatty as well as the steatohepatitis, and also different stages of fibrosis. So basically, for diagnosis, if you're talking about diagnosis, it should be for steatosis, it should be quite straightforward. So now in hospital, they have for example, you can use the cheapest way is ultrasonic, the cheap one. Of course, the MRI can do it. That's has already, hospital they can directly do it. I use the non-invasive methods. But for the severe status, or we can call it major NASH, it's steatohepatitis. So let's say directly, it's like the amber warning for the patients. And at the moment, the golden standard is lethal biopsies, which is invasive method. That's why we develop those non-invasive method. Also for the steatohepatitis, I think let's say it's also many pharmacy companies are interested, because at the moment there are no any approved therapeutics for the disease. So I know several companies like Armini or something, they try to invest not money in this area for treating the NASH, for treating the steatohepatitis, because right. for the steatosis, you can do the exercise, you can, that's probably you can control, you probably can reverse it. For NASH, you can also reverse it, but it's not so easy, and was highly associated with the high morbidity and mortality.
Right. Yeah, what about the specific potential biochemical plasma markers? I mean, besides AST, ALT, and some other routine.
Oh yeah. So that's a lethal enzyme. So it's trying to tell us whether the lethal is functional well or not. Those enzymes are not specifically not only specific for the MFD. It can also use for some other lethal disease, for example, like the hepatitis.
Right.
What do you mean by hepatitis, for example? Yeah.
Okay. Thank you.
Thank you, Alex.
I think if there are any questions, I don't see any questions in our chat box. So I think we'll probably just expect potential questions or comments by submitting publications from other people and exploring this field. But I think for that, I would like to basically thank both speakers for their time and wonderful talks, all the webinar participants, and of course, Nutrient Journal for organizing and supporting our today's meeting. I do hope during that short time we were able to summarize current knowledge in fatty acids' role in cardiometabolic complications and increase awareness for MFLD among healthcare providers. And finally, I encourage everyone to contribute to our relevant special issue by submitting their research articles. And thank you very much again, and please contact me or our speakers for any further questions if you have any. Thank you.
Yeah, thanks very much for organizing, Alex, and also for the other staff from the MDPI contributed to this event. Thanks very much for everyone. Thank you.
Yeah, thank you. Yeah, we'll definitely exchange emails. And so Tanya, let us know. I guess we can just wrap up and end today's webinar.
Thank you.
Thank you. Cheers.
Thank you.
Thank you. Bye.